Again, so let's take a look at the cations. You know, we call it the unknown mixture because we don't know if it's present or not. You know, qualitative analysis is different than quantitative analysis. Quantitative analysis, you care about how much is in there. But your unknown could contain, what are the anions that it could contain? It could contain sodium ions. These are going to be in an aqueous solution, so let's write AQ. What other ions are present? Do you have your lab manual? Can you open up your lab manual to qualitative analysis? Just take a look. Normally I would, maybe you're not in the habit of doing this yet, but normally I would have expected the lab to be prepped for today in your notebook without having to tell you or announce it. But that's usually not the case. I normally have to tell you or tell the student in general to prep it. But for now, if you haven't heard about the lab, just take a look at the syllabus and see which lab we're doing and then just prep for that lab. So we're back on schedule now. And so today we're going to just go through it. But for next time, you'll want to just do a little prep work. But just take a look at the procedure part, and actually what you want to do is you want to focus on the flow chart, because the flow chart is going to give you the big picture of what's going on. And so if you take a look at the flow chart, we can kind of visually see what's going on, because it's so easy in this particular experiment to get lost. You know, I'm on step 5A, okay, what do I do next? They have no idea what they have or where they're at. They just know that there's step 5A in the paragraph. But what we want to do is we just want to briefly be able to see what the overall experiment is, and we can do that using the flow chart. Now, there are going to be multiple flow charts in here because it's kind of a long experiment. But if we take a look, what ions are potentially present? Sodium. We'll just go sodium, ammonium, silver, iron 3, aluminum 3, chromium 3, calcium, magnesium, nickel 2, and zinc. All right, so how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are going to be 10 cations that we're going to try to detect the presence of. And as far as the anions go, the anions that we're going to test for nitrate, carbonate, I think, what else? Sulfate, chloride and bromide. Okay, I don't know for chloride, bromide, and iodide. Well, one thing is we can't have everything in there. The reason we can't have everything is because, for example, silver ions like chloride ions, that would be a metathesis style reaction. And so if we have silver ions, we can't have chloride, we can't have carbonate, we can't have sulfate. And that goes for some of the other species as well. And so we have an unknown and a known solution. Before we do the unknown, we're going to do a known. And we're going to have two unknown solutions for practice. And so we practice with known solution first. And we have two known solutions. We have the cation known. The cation known contains all 10 cations. Contains all 10 cations and nitrate. Nitrate is not reactive in the metathesis sense, so it works out okay. And so when we go through the tests, it should work for all the ions. We should expect the results that are outlined in the manual there. And then we have an anion known. The anion known would contain all the anion stuff. And so we practice with this first. All right, when we practice with the known first, you can work with a partner if you like, but you have to be careful because if you work with a partner, you have to pay attention. You have to pay attention because on the unknown, you work by yourself. In other words, this is individual work only. All right, when you work with the practice solutions, you can use all available resources. When you do your unknown, however, you can't work with all available. In fact, you can't even use your lab manual. You know, the only thing you're allowed to use with the unknown is your lab notebook. So, lab notebook, no lab manual. So let me write that here. No lab manual, notebook only. Of course, you could write whatever you want in your notebook, but that's it. And so we're going to go through the cation known solutions, and then make sure we understand those. If we get some ambiguous results, the best thing to do is just repeat certain steps or start over. So you see what's going on. Now, there are two types of tests that we're going to do. And so we have individual tests. The individual test, we test a sample of unknown directly for specific ions. Like, for example, our unknown, we're going to test for, first one would be for sodium ion. And so what we do is, this unknown is an aqueous solution, so we just take a little bit of this unknown and test it for sodium. We don't want to use all of it for one test, because then we don't have any left over for all the other tests that we have to do. And so we have to conserve our unknown for additional testing. And so here we're going to test it for sodium. If it comes out positive, then we have sodium present. If it comes out negative, then a negative test, positive means it's present. A negative test means it's not detected. A negative test does not mean it's not present because it could be so dilute it's hard to detect. Some of these you need pretty high concentration for, not for sodium, but some of the other tests you need a fairly high concentration, and if you don't have that high concentration, it might be present, but you just don't see it. And so negatives, it just means it's not detected. Could very well not be present. So anyway, the individual tests are for sodium, for ammonium, and then all anions. That is nitrate, etc., the anions. However, for these cations, silver through zinc, these ones we don't do an individual test. We do a series of tests and separations. So first we're going to look at the individual tests here. The test for sodium. The test for sodium, let's take a look at that. It's pretty simple, but it being pretty simple means it's subject to false positives. What I mean by false positives is you might not have any sodium in your unknown sample, but it's so easy to contaminate your unknown with sodium ion. And we could see that. So here, let's do this. Everything you touch leaves a residue of sodium ions on there. And so if you were to touch this piece of metal here, I left some sodium ions there, and the test is so sensitive it can detect it. And so let's see what the sodium test involved. The sodium test involves just introducing some of our unknown sample into a flame like this. And so if there's sodium present, we should see yellow color in the flame. Do you see that yellow color? That yellow color is sodium. So I just tested positive for sodium on my paper clip. And did you see how bright that yellow color is? That's pretty bright. That means this. Let's see if I can get some. And so what we're going to do is this. We're going to do the sodium test much later. The sodium test is done in this way. We take a wire that's resistant to corrosion. Now this paper clip isn't so resistant to corrosion. It's already turning black from oxidation. And so what we'll do is we'll get a piece of water like nichrome. Nichrome is an alloy that's pretty resistant to oxidation, or platinum. Platinum is an element that's really resistant to oxidation. And then what we're going to do is we're going to first clean it. But your platinum or nichrome wire is going to be highly contaminated with sodium like this. And so what you have to do is you spend, like some people spent an hour and a half burning the sodium off their piece of wire. It's difficult. There's certain tricks that can help you speed it up. Let's see. This is a paper clip. Let's see if I could burn it off. It's getting hot though, so let me grab some tongs here. Obviously the tongs, what do you think the tongs are going to do? Tongs might give a whole bunch of different colors because people spill different salts and different chemicals on there. Sodium will give a yellow flame like this. Other elements give a different color flame. And so let's see if I can burn some of this off. You see the color starting to fade? Can you see that? Compare it to this. Now here I'll just wipe my fingerprint on the opposite side. I'll just grab it here. Burns, you gotta watch out for burns. But now I have a lot of fingerprint residue on here. Let's take a look at this flame. Oops. Here. Do you see how intense the color is there? We don't want any of that color because that would give us a false positive for sodium. Let me grab the middle here. Let's flip it over here and see. And so what I want to do is I want to clean it. Well, there are people standing around so long holding their wire here, and it was still burning so brightly that what they did was they got a clamp. They clamped it, here with a 3-prong clamp. They clamped their little wire. It's attached to a piece of glass, and left it in the burner like this, and came back in an hour and checked it. and then came back another half hour later and it was still dirty. But now take a look at the color. Do you see that now? Do you see much yellow from the sodium? No. Okay, once the flame is completely clean, that is, it's not imparting any yellow to the flame, now we can test. Okay, now test some unknown. Okay, I don't have much color there. See that? Okay, so what I'll do is I'll test some, what do you think? Does tap water have sodium ions in it? Probably. Let's check it. And so this would be a qualitative analysis test for sodium in tap water. What I'll do is I'll get some tap water on here and then introduce it into the flame and see. Do you see that? Does tap water have sodium in there? Yeah, definitely. Tap water. In fact, did you know glass? Does glass have sodium ions in it? It turns out Pyrex glass does also have sodium ions. And so if you're doing highly sensitive, there are even more sensitive tests for sodium. We can use sophisticated instruments and spectroscopy to do it. But if we're really testing for sodium properly, we do not use glass. Do you know what you use instead of glass? Use like plastic. You use plastic beakers, plastic flasks, plastic whatever. I used to use polyethylene or Teflon. Polyethylene is way cheaper than Teflon, so I used to use polyethylene for storing solutions that I did not want to contaminate with sodium ions. Well, what's the chemistry behind this? And so, well, you know, cleaning this wire, let me tell you, cleaning this wire is such a pain that we have to do 2 flame tests. We're going to do a flame test for sodium, which is that bright yellow, and we're going to do a flame test later on for calcium, once we isolate calcium from all the others, because the others might impart a flame, like chromium, copper. We're going to test for calcium. And calcium, sodium's so easy because you get this bright yellow flame, but calcium is so hard. Calcium's so hard because if there's a tiny bit of sodium, that tiny bit of sodium will completely drown out any calcium signal that you might see. That is, the calcium signal is just going to be what we call a brick red flame. This brick red flame lasts about 1 second. And so when you test your sample, you see a brick red flame and it's gone. It's totally vaporized. You know? And so what you have to have is you have to have an especially clean wire. And so the best thing to do is this. The best thing to do is wait to test the sodium, because this is an individual test. You can test it anytime you want. You don't have to test it in the first step or in order. So what we do is we wait, because we only want to clean this wire once. And so we'll wait, and then we test first for calcium. Look for the brick red flame. It doesn't last very long. And then once we're done with the calcium test, just burn it off, it's pretty easy. Then we'll test a new sample for sodium, just quickly. And you got to watch out for contamination. Okay, this flame test is not so crazy sensitive that we have to worry about the glass. I mean, the glass should be clean. Obviously, you don't want to rinse with tap water, because tap water does contain sodium. All right. So what we're going to do is we're going to look at the chemistry of what's happening for sodium. So let's go ahead and take a look. And for sodium, we look at, you know, what we're observing, and so we'll call this observation. The observation is we take some unknown aqueous solution, we put it on the wire and throw it into the flame. And we get, you know, a bright yellow flame. And that would be a positive for sodium. And positive test for sodium. And then what we'll do is we'll take a look at the chemistry that's happening by an equation. And so the equation for this is we got sodium ions in the flame. This is AQ. And then we vaporize those, you know, so we'll get sodium ions in the gaseous state. the sodium ions in the gaseous state, you know what a flame is? A flame is what we call a plasma, and a plasma is what happens when there are violent collisions in the gaseous state. When there are violent collisions, electrons get knocked off, and so we have free electrons and ions in the flame. And so there are different parts of the flame. There's the what we call like a reducing part of the flame. The reducing part of the flame is the kind of the gaseous rich area in the center. Then we have the oxidizing part of the flame. Well, the sodium ions can get reduced in the flame to sodium, atomic sodium gas. So the flame can supply electrons to it because flames, being a plasma, are partially ionized gases. And then what happens here are the collisions, and so we get sodium in the excited state. So originally it's in the ground state, and then it gets to an excited state, which means the electrons get promoted to higher energy orbitals. But those electrons don't stay in higher energy orbitals forever. Those are going to drop back down to the ground state and emit an H nu, or a photon. This photon has a characteristic orange-yellow color that you can see in sodium street lamps. So this would be it. So that would be the equation for that. But again, we don't want to do the sodium test until well after calcium, even though it's like the first test or the second test in there. All right, so this is the reaction. Now, the next test we're going to look at is for ammonium. Again, ammonium is an individual test. The individual tests are best saved for last. They're best saved for last because they don't take much time and commitment to do those versus these test series that we're going to be looking at. And so the next test will be for ammonium. And so if our unknown contains ammonium, what we're going to do is we're just going to add some ammonium. What's a chemical property of ammonium? Well, ammonium AQ. Ammonia, NH3 would be a gas. Ammonium should be an ion. Most likely it's a weak what? It's not it's not a weak base actually. It's not a base at all.
No, it's a weak acid.
It's a weak acid. Ammonium's a weak acid. And so what we're going to do is we're going to just add some sodium hydroxide AQ to this. We add some sodium hydroxide, and what does that form?
Ammonia plus water.
Ammonia plus water. Ammonia is highly soluble in water, so we're going to get some ammonia in here. It's going to be ammonia AQ. And how can you detect the presence of ammonia? Well, we have a test for bases. Do you know what the test for bases is? Litmus paper. However, if we were to test this solution, it's going to turn blue for basic easily because we're going to have excess hydroxide from the sodium hydroxide. And so we need to separate these two bases. We need to separate the ammonia from the hydroxide. Do you know how we can separate the ammonia from hydroxide? Well, the acid will attack both because both of these are bases. So the acid will attack ammonia and the acid will attack hydroxide. First, the acid will attack hydroxide because this is the stronger. But eventually, once all the hydroxide's been reacted, then it'll attack the ammonia. So adding acid won't do it. Try to think of another way. Let me give you a hint. In this case, we aren't going to use chemical properties. You know, we'd like to use chemical properties to separate the two, but in this case, we're going to use physical properties. And so, how are we going to separate the ammonia from the hydroxide? Uh-huh.
Vaporize it into ammonia gas.
Yes, vaporize it. And so what we're going to do is we're just going to heat this up. And the symbol for heat is this little triangle or delta. We heat this up, and what that's going to do is it's going to drive off ammonia. The hydroxide is going to stay in there, and so the ammonia is going to come off as a gas. Now we have to detect the presence of ammonia gas. One way of detecting the presence of ammonia gas is just smell. You know, you could smell it. But we aren't going to smell it because smelling chemicals can be dangerous, especially if you're producing something toxic. So we don't want to smell it. What's another way we can detect the presence of ammonia gas? With litmus paper. And so what we're going to do is this. Well, I guess you could hold a piece of litmus paper in the air above it, right? That would do it, but we don't want to hold a piece of litmus paper there because litmus paper, one, you know, if it's wet litmus, it'd be better than dry litmus. You know, you'll have probably a faster response with that. And so the way we're going to test a gas with litmus paper is actually not too difficult. And so we're testing for base. So we want red litmus paper. Bases will turn red litmus paper blue. And so I have a piece of litmus paper here. And there aren't that many gases that are basic. You know, like, is oxygen basic? No. Is nitrogen basic? No. But ammonia is basic. So I'm going to put a piece of litmus paper on the underside of the watch glass, but it doesn't stick there unless I wet it. Now, if I wet it down, then I have a piece of litmus paper stuck on the bottom of the watch glass. And then now I can test, like, if I exhale on this, is CO2 acidic or basic? CO2 is acidic or basic? Acidic. So if I exhale on this, it'll stay red. It's not going to turn blue. Whereas if I had a piece of blue litmus paper stuck on the bottom and I exhale on it, it'll turn red. If I continue to exhale on it. Right? But ammonia will. And so what I got to do is I got to be careful. I got to just let the gas come into contact with the ammonia. I'm going to trap the ammonia inside the beaker like this with the watch glass so I can concentrate it there. And what you're looking for is this to gradually turn blue. It should be a uniform blue color because as the acid. What often happens is people will splash. They'll splash some solution. If they splash some solution on, that solution contains a strong base, hydroxide. Obviously, hydroxide is going to turn red litmus blue. And so we have to make sure the hydroxide doesn't come into contact with this, only the ammonia gas. Now, if the litmus turns blue, you know, we're going to test the gas with blue litmus. And so if the if the red litmus turns blue, then we have a positive test for ammonium. Ammonium was present in our original sample. Otherwise, this sequence wouldn't happen. And so what we do is we could write an observation like this. The observation is going to be, we take some unknown sample, AQ, and then we add some sodium hydroxide to this. We heat this up, and then we check with red litmus. Red litmus goes to blue. And we're positive. The equation for this, okay, the equation would be something like this. You take your ammonium and your hydroxide. You're going to form ammonia and water. The ammonia is AQ, and so what we need to do is we'll need to heat it up to drive it out of solution to get ammonia gas. Now the ammonia gas we're going to test with litmus. And so litmus is actually, do you know, red litmus is actually a acid. And it's an organic acid, like the carboxylic acids, and its formula is kind of big and long. So what chemists often do is they'll just abbreviate it. You know, the anion for litmus we'll just call LIT minus. Cation's H plus. And so this is the acid form. This is red. Now, bases will pluck that proton off the acid here in a Bronsted acid-base type reaction. And that's going to convert ammonia into ammonium plus LiT minus. LiT minus is blue. And so it depends on the form. When I look at this conjugate pair, acid-base, they're different colors. The acid form is red, the base form is blue. So that's the conversion. So that's the equations for the chemistry that's happening in this particular reaction. Okay, again, this is an individual test. The anions are going to come at the end, so I'm not going to do any of the anions. Let's look at the remaining cations. We have 8 remaining cations. And the 8 remaining cations, we can't do individual tests for. Individual tests for these 8 remaining are difficult. And the reason they're difficult is because sometimes the chemistry, the chemical properties overlap. And so if you're testing for one ion, other ions do the exact same thing. And because of that, those are called interfering ions. And so what we have to do is we have to isolate each ion from all the other interfering ions so that we can test for it individually. And so what that means is in the sequence, the 8 remaining cations, which would be what, silver, what else do we have? Was it silver? Iron 3. Aluminum 3. Chromium 3. Magnesium. Nickel. Zinc 2. One more. All right, now the easiest way to see this next series of experiments is they're going to be separation and conformation steps, or separation and detection steps. And so what we need to do is we need to isolate things based on chemical and physical properties. And so these are all aqueous ions here, so I'll write a dashed border around there. And so we have a solution with these cations in there, and then we're going to test these. And the problem is this. We go through a sequence, and we have to do this in order. We cannot skip ahead or jump back easily because each step relies on the previous step. And so we have to do these in order, which means if you get to the final step, now this has happened many times. You get to the final step and you don't have much because you've gone through so many steps. You lose a little bit here, lose a little bit there, right? Things happen. You get to the last step and you're mixing like this, mixing these chemicals, and then you just punch the hole through the bottom of your test tube. And you go, I didn't push that hard. Why did I punch a hole through the bottom of the test tube? You punch the hole through the bottom of the test tube because everybody's been doing this. And what happens is that stresses the bonds. It tries to push the atoms and distort bond angles. When the bond angles become distorted, it becomes brittle. And so glass can become very brittle, where just the slightest touch will crack it. If you're worried about brittle glass, then this is what we do whenever we're worried that the glass is brittle. In other words, the glass has structural stress in it. Make sure you throw the matches away once they cool down. But what you can do is a process. It's called annealing. Annealing is just to soften it just a little bit, so that the bond can, because you're tweaking on the bond, so the bond angle is getting all screwed up, and so you just anneal it a little bit so the bond can relax to its minimum energy configuration, its angle. Silicate's a tetrahedral bond angle, so 109. Glasses are mostly silicate type glasses. And so what we do, we don't heat it on the hard part, because if you heat it on the hard part, it'll soften so much it'll distort the glass. You want to heat it on the soft part of the flame, above the cone, like this. Does this glass have sodium in it? You see that? Testing positive for sodium here. It could have sodium in it, or it could have sodium on it. Pyrex has sodium in it and on it. So it depends on how we clean it. How about the tongs? I'm afraid to put the tongs in here, because who knows what people splashed in here. Oh, the tongs are surprisingly, no. Some sodium on the tongs too. In fact, everything, sodium. Sodium is pretty ubiquitous. Now, if you were to do this, one time a person was doing this and said, "Oh, is it okay?" They're handing it to me, so I went out to grab it, and I grabbed it by this end. I got like blisters on my thumb and finger. So it's so hot. You can't tell it's hot, because it looks just like cold glass. And so normally we have a ceramic plate. On the ceramic plate, you point the hot ends away from you, so you just reach for the close end, the cold end. Right? But you might want to do this when you have a break or have spare time. Especially, at the beginning it's no big deal. Start over. But if you reach the end of the experiment and pop, and your solution goes all over the counter and it's contaminated, you have to start over. You have to go all the way back to square one, the start. And unfortunately that's happened. And so this is the only reason I bring up annealing the glass, because if you anneal it, we don't have to worry too much about popping a hole at the bottom of that. All right, so what we have to do is we have to figure out how we're going to separate these. So what's the first step in the flow chart?
Color and flame.
Okay, now that's an individual test for sodium. Fast forward. Fast forward until you see the 8 cations in a dashed box like this. I don't have a lab manual. I loaned out my lab manual and never got it back, unfortunately. So I have a lab manual on request. I should just go buy one and break down, but I'm looking down.
I think it's precipitate something with HCl.
All right, precipitate silver with HCl. In that procedure, it says to add 3 drops of HCl, right? 3 drops. If you go back to the procedure and read it. Is it 3 drops? Is that correct? Or 2 drops? Or 1 drop?
Yeah, you need a centrifuge as well.
We have centrifuges.
And yeah,
2 drops?
yeah.
2 drops of HCl. And so in this, the way I do this is I don't bother writing any procedure. I write a flow chart, or I make a photocopy of the flow chart and just tape it into the lab notebook. And here I write the recommended 2 drops of HCl, 6 molar, right? It's 6 molar. And this. But the thing is, okay, there are people who are really good, really precise in lab. So if the procedure calls for 2 drops, they get 2 drops. They don't get 1 drop, they don't get 3 drops, they get 2 drops. And you would say, okay, you should, give that person a star because they did the procedure correctly. Right? Well, no, wrong. Wrong because of this. This procedure is a one-size-fits-all procedure. Let's say, okay, I'm going to go buy some clothes. I'm just going to go buy the one-size-fits-all clothes, right? And so if you get the one-size-fits-all clothes, it might work perfectly, or it might be too big or too small. I don't know if it stretches that much, but let's just say it's either going to be too big, too small, or perfect. Well, 2 drops is the one-size-fits-all chemical procedure. It might be too big, or it might be too small, but they had to come up with a one-size-fits-all procedure. And so the person who adds 2 drops is the person who doesn't really know the lab well enough. Because what you have to do is you have to adjust the procedure depending on what the goal is. What is the goal of this particular step? Ian said what the goal is. What is the goal? Precipitate silver chloride. Are we going to precipitate anything else or just silver chloride? We're just going to precipitate. It turns out that all the other chlorides will iron 3 chloride precipitate. No. In fact, the only chlorides that would precipitate are silver. Chlorides are all soluble except for silver, mercury 1, and lead 2. It's good memory. It's good. So silver, mercury 1, and lead 2. Everybody should, that should be easy. It should be automatic. Do we have any lead or mercury in our unknown or known? No, so we lucked out. If we have lead and mercury, we have a whole bunch of additional steps that we have to do in this separation, but this is the easy one. If you had Chem 4, you've already done the complex one, maybe even more complex than this one. But anyway, we get a precipitate. The precipitate should be silver chloride. Now let's say we had lots of silver in here and 2 drops wasn't enough. If we had lots of silver in here and 2 drops wasn't enough, that means the silver is going to contaminate our what we call supernatant or filtrate. We call it supernatant because we're just going to decant it off. And so over here, we hope to have the iron 3, the aluminum, the chromium, the magnesium, etc. But we don't want any silver here. If we get silver over here, do you know what that means? That means that is going to interfere with subsequent analysis here. In other words, if silver some of the silver manages to escape precipitation, it's going to screw up your experiment. And you're going to get really confusing results because of that. And so this is what we do. We keep adding HCl. 2 drops is a guideline. But we keep adding HCl until we've maximized precipitation. Well, how do I know if I've maximized precipitation? Because what's going to happen is this. Silver chloride is going to form a cloudy white suspension. And so as you're adding HCl, you can't tell, is it getting cloudier or is it the same? Because it's so cloudy, you can't tell if it's a little bit more cloudy or not. And so what we'll do here is this. When we do this, we want to make sure we absolutely get all the precipitate. And so what we're going to have here is just, it's going to be cloudy with precipitate. And so if I add one more drop of HCl here, I can't tell. And so, fortunately, we have these things here in the hood. This is a centrifuge. And so what we'll do is we'll put our test tube sample here. Now we have different size test tubes. And so we have different size inserts here. You have to make sure you're using the right insert, otherwise your test tube might be difficult to recover out of here. Then we have to counterbalance it. You know, if it's not counterbalanced, then it's going to start rocking quite a lot. And so let's do this. The way we counterbalance it is we just set up a blank test tube, the same size except just with DI water rather than solution. And so let's say I have my cloudy white PPT, and then I'll get like a blank test tube with just some DI water. Fill it to about the same height here. Okay, then I'll put it in here to the centrifuge. I'm going to make sure I put it in the right one. It looks like, yeah, I'm okay here. I'm covered. Otherwise it might sink down. This is what it's going to look like if it's not balanced. And so there's a timer on here. I just let it go to max RPM. Okay, did you hear the noise on that? Okay, this one has a break, and so we can actually break this one. When we break it, you just use a paper towel. You don't want to bring it to an abrupt stop, because abrupt stop will dislodge the precipitate, but you can bring it to a gentle stop. Okay, that was not balanced, but this is going to be balanced here. And so on the opposite side, I'll just put in my blank test tube there. And then let this hit max RPM. So you just listen to it. Do you hear the difference in sound? Yeah, this is balanced. And then once it's hit max pitch or frequency, that's enough. You just get it to the maximum and then just twist it off. Then we'll just break it. Like this, slowly. You can break it rapidly and then just bring it to a gentle stop. Okay, so after centrifuging, what's going to happen is this. After centrifuging, all that precipitate is going to be packed down at the bottom of the test tube, like this. And so we should have what we call a CCS up here. Do you know what CCS stands for? Clear colorless solution. Actually, it might not be colorless. It might not be colorless because do any of these have color? Yeah, iron has color. You know what color iron is? Iron 3, it's yellow. Silver, colorless. Aluminum, colorless. Chromium, blue-green. Magnesium, colorless. Nickel, green. Zinc, colorless. Calcium, colorless. So it might not be a clear color. It should be clear, but there might be color in here, depending on what ions you have in here. All right, now we can test for complete precipitation. Whenever we do a separation like this, we always have to make sure we have complete precipitation. And it doesn't matter how many drops you add. You know, if you have to add 20 drops, then add 20 drops. You have to be flexible in that way. And so you just keep adding. You keep adding until when? You keep adding until you're done precipitating, because we got to make sure we get rid of all the silver. If the silver gets in here, you've just screwed up the rest of your test, basically. And so what we'll do is we'll just add a drop of HCl. And look, if we add a drop of HCl, HCl is more dense, so actually I'm not sure. It could be more dense. It should sink. And we watch the drop as it sinks. And we look for cloudy precipitate forming. If cloudy precipitate's forming, then we got to keep adding. We keep adding until it gets so cloudy we can't see it, or it stops. Right? And so we just keep repeating this until we're sure we've gotten rid of all the silver. Does it make sense? And so this number of drops is just a guideline. It could take 20 drops. Depends. How much silver do you have in your unknown? Well, it's an unknown, so you're not even supposed to know how much silver you have in your unknown. And so here, likewise, if nothing precipitates, let's say after 2 drops nothing precipitates, you could add a 3rd drop to be sure, and still nothing precipitates, then do you want to keep adding? Pretty soon you have 5 milliliters, 10 milliliters, a gallon, 2 gallons, 10 gallons of HCl, and nothing precipitates. Then you should have stopped long ago, because if you don't see anything precipitate, then stop right away. Because if nothing's precipitating, then you don't want to add so much HCl, because what you have to do is you have to undo that. And so if you add too much HCl, the HCl can interfere in subsequent tests. And so we have to be careful. We don't want to add too much. We don't want to add too little or too much. We want to add just the right amount. And so that's why people are very precise with instructions don't do well in this lab. You have to be flexible and adjust it, and you also have to know what you're trying to do. And so what are we trying to do in this particular step? What we're trying to do is we're trying to do a separation. We need to isolate silver from the rest of the group. And the reason this works is this. And so this would be the observation, and then I'll let you work out the equations later on, but I'll just do the first series here. And so for this particular branch here, we have this. The observation, OPS, is we take our unknown and we add HCl to it, and we get a white PPT. This is observation number 1. And the equation for this is going to be this. Our unknown must have contained silver ions, because the silver ions will react with the chloride ions in HCl to form a white precipitate of silver chloride solid. That's the equation. Now, what about all the other ones? Okay, all the other ones would be iron. Iron 3 plus with chloride. Does it give us anything here? No, and so this is important. This is an important chemical property. If iron 3 plus also reacted with chloride, then it may or may not work, this procedure. We'd have to do something else. So this is important. Even though there's no reaction, we're still going to write these down. It's Nr. Chromium gives us Nr. Magnesium, nickel, zinc, and calcium with chloride all give us Nr. I'll just write it out. And so the only thing that reacted was this, but we have to know the chemical properties to know that nothing else is going to react. Okay, now what happens is this. What we're going to be left with a test tube like this that has silver chloride at the bottom, and then above this it has the supernatant. The supernatant is this, and the precipitate is this. So we got the precipitate down here. And so how do we separate the supernatant from the precipitate? The way we're going to separate the supernatant from the precipitate is this. Use I'm just going to use water. The way we're going to separate it is we're going to get a clean test tube. The clean test tube, do you want to use tap water as your final rinse? No. You're going to use DI water. Do they have to be dry? They don't have to be dry. You don't have to dry them. You can leave them wet with DI water. And so what we're going to do is we're just, not too much because otherwise we'll dilute it, and dilute unknowns are harder to detect. And so all you're going to do is you're going to pour the supernatant into the clean test tube like this. So just pour it. Okay, hopefully that leaves a plug of precipitate here, but that plug of precipitate, can we get all the supernatant over? Okay, so there are a couple of tricks you can try to get the maximum amount of supernatant over. One is you could use, do you have plastic pipettes in your drawer? You should have plastic pipettes, and then, but these pipettes are pretty long. And so what you could do is you could reach into the test tube and then just suck the top of the solution off and then transfer it this way. That's one way. But are we going to be able to get it all? No, we're not. We aren't going to be able to get it all. That means, you know, we'll try to decant as much of it as possible. And so we try to decant as much as possible, and then what we end up with is this. We end up with precipitate like this, and there's going to be a tiny amount of supernatant, or a small amount, might not be tiny, a small amount of supernatant on top that we just can't kind of transfer over because otherwise we get precipitate to transfer over as well. And the supernatant is contaminated with all these ions here. And that can interfere with subsequent tests here. And so what we're going to do is this. We're going to wash our precipitate because it's contaminated with dirty water. So we're going to wash it with DI water. Or HCl. Depends on the step. All right, but the thing is this. So we wash it. How do you wash it? You just pour some water in here and then stir it up and then centrifuge it. Now the first wash is going to be contaminated with all those ions, right? But here's the situation. The situation is this. As we go on to step 50, step 51, step 52, as we go on to those steps, if you're not careful, you could lose all your ions in each of these separations. So by the time you get to step 52, there's nothing left. Just water. And then you have to start over again. And so to prevent that from happening, the first wash is always combined with the supernatant. That way we don't lose any. We might also do the second wash. The second wash we might combine with the supernatant too. The third wash we don't want to. For sure the third wash we don't want to because the third wash is going to be mostly DI water. And if we just add more and more DI water to this, it becomes more and more dilute. The more dilute it is, the harder it is to detect the ions. If your unknown solutions are becoming overly dilute, then what we have to do is boil them down. You know, it's like your crystals. You know, if you aren't getting any crystals, you got to boil down the liquid. Maybe they're all dissolved. The same thing here. If it's getting way too dilute, it's going to be hard to detect. And so, this is a separation step. A separation step means we have to get maximum precipitation. In other words, maximum precipitation is called complete precipitation. Later on we'll know what complete precipitation means. But we're going to get complete precipitation of the silver, and we're going to make sure it's completely precipitated. That is, we can't get any more. Okay, once we get the complete precipitation, then the next step is to wash and not discard. Wash and then combine. So we get separate, and then wash and discard. You know, so your second washing or your third washing you'll discard rather than combine. All right, now what we should do is we should stop here and say, well, this is enough, but you know, we don't know because white precipitate, if we had any lead in here or if we had any mercury 1 in here, then this precipitate need not be silver. This precipitate could be white lead 2 chloride, or this precipitate could also be white mercury 1 chloride. So to confirm that it is silver, we're going to, silver chloride behaves differently than lead and mercury chloride when exposed to ammonia. And so what we're going to do is we're going to do what's called a confirmatory test, or confirmation test for silver chloride. We've got to make sure this precipitates silver chloride and not some other insoluble chloride, i.e. lead and mercury. The confirmation test involved this. It involved dissolving this in aqueous ammonia. Are we using concentrated ammonia or dilute ammonia? Just go to the flow chart and see. Does it show it in the flow chart? Maybe, maybe not. We're going to follow the silver chloride branch. Six molar ammonia. Now, okay, how much ammonia do we add? 4 drops. Smaller. 4 drops is not the correct answer. Why? How much ammonia we add is just enough to do what we're trying to accomplish in this step. If 1 drop does it, then don't add the extra 3. Because adding the extra 3 means you have to undo those extra 3. Undoing those extra 3 or 10 or 15 drops isn't easy sometimes. It's very difficult to do. And that means you have to think about how you can undo it, because the procedure certainly isn't going to tell you how to undo it, right? And so what we got to do here is not to add 4 drops, it's to add, well, what are we trying to do here? Well, we're trying to go from a solid box to a dash box. Is this a dash box here? And dash box means, is it a solid or a solution? It's a solution. What we're trying to do here is we're trying to form this. Can you name that ion for me? There were 4 what we call ligands that have special names that you have to memorize. NH3 is one, H2O is another, NO is another, and CO is another. Do you recall their name? No. Yeah, this is a complex ion. So, though I did talk about nomenclature a little bit. You're going to see a bunch of complex ions, but I'll let you have some time and think about it. But we'll move on here. What are you trying to do in this step? what you're trying to do is you're trying to dissolve the precipitate. This precipitate dissolves in ammonia. Right. Okay, since the precipitate dissolves in ammonia, we want to use the minimum amount. So if it dissolves in one drop with stirring, then stop there. The minimum amount required to dissolve it is the correct amount of ammonia, whatever that minimum is. All right, and then once all that dissolves, it should form a CCS. So we should go from white precipitate to a CCS. And then what we can do is we can just add some nitric acid, 6 molar. I'm not even going to put the amount here because, you know, I don't need the amount. I just need to know 6 molar nitric. How much do I need to add? I need to add, well, what am I trying to do in this step? Can you look at the flow chart and see what's in the next box? Is there a next box, or is it done? We aren't even going to bother. I know it says add it until it's acidic to litmus. And we could do that, but it's not necessary because the purpose is not to acidify the solution. The purpose is to do what? You know, the purpose is not to get blue litmus to turn red. The purpose of, and the situation is, if you have ammonia, ammonia is what? An acid or a base? A base. And if it's a base, it's going to turn red litmus blue. Blue litmus will stay blue. And then once we get all this to dissolve, it's going to take excess ammonia to do that. Once we get it all dissolved, this solution is very basic. And so we're going to add acid. The acid is going to neutralize this basic solution. Now, the purpose is not to neutralize the base. The purpose is to, what's the next box? It should be in your flow chart. Maybe you're not looking at the right flow chart. There are multiple flow charts in here. What's the next box after this complex ion?
It goes back to the silver chloride.
It goes back to silver chloride. Good. What page are you looking at, Ian?
94.
Page 94. Take a look at page 94. And then it goes back to silver chloride solid here. And so the purpose is not to turn blue litmus red. The purpose of the HNO3 is to reprecipitate out silver chloride. So what are you looking for? Are you looking for blue litmus to turn red? No. In fact, I'd skip that because that to me is a waste of time. It's a total waste of time. You skip that step, you'll save about a few minutes, 5 minutes maybe, more or less. If you really do need to test with litmus, what you do is you dip your stir rod in there and then put a drop on litmus paper. Don't stick your litmus paper directly in here. But even though, you know, I say this, people still feel very uncomfortable doing that, and they'll still. You're welcome to test it with litmus. You know, don't get me wrong. So if you feel uncomfortable skipping steps, don't. You know, just follow the procedure. If this is very confusing to you, just follow the procedure. So you should do. But for me, you know, I wouldn't bother testing for litmus because I know what I'm trying to do. What I'm trying to do is I'm going to try to add HNO3 and try to get cloudy white precipitate to form. So I'm going to keep adding HNO3 until I see a white precipitate. If I don't see a white precipitate, then something went wrong. You know, if I got to this step and I don't see it. And typically what went wrong is that you added way too much ammonia to this. And therefore, you have to transfer it to a beaker and then start adding lots of HNO3. Or, you know, sometimes people add the 15 molar ammonia. They add the 15 molar ammonia, then you can't do it with 6. You got to do it with 15 molar nitric. Otherwise, the volume starts growing, and pretty soon your test tube's going to overflow. Okay. So lots of places to screw this up, potentially, but what you do is you just keep in mind what you're trying to do here. And so let's write the equations for this. The equations for this and the observations are here in the flow chart, but this is what you're going to have to do for the report for this. And so we'll follow along on the left branch there, and then just write our observations. So we take the precipitate that we generated from 1, this would be observation 2 here, and then add ammonia to that, and then we get a CCS. And the precipitate from 1, let me write this equation out, is silver chloride. Does silver chloride dissolve in water? No, it's insoluble, right? So silver chloride is highly insoluble in water. And so what that means is that, you know, if I look at this reaction here, this reaction is called the dissolution reaction. If I look at the dissolution reaction, it's heavily favored to the left. You know, in other words, K is very small for this. K is actually 10 to the minus 10. 10 to the minus 10 means, you know, 1 part of product to 10 billion parts of reactant, roughly. You know, this is one way of visualizing this. And so, you know, very little of this silver chloride dissolved. But you guys recall coupled reactions. What's the strategy in using coupled reactions? We try to find a reaction that'll react with one of the so for coupled reactions, we try to find something to react with one of the what? Or can you give me an example of a coupled reaction? Oh. I didn't. I was thinking I'm not going to ask a coupled reaction question on the test because I thought it was kind of easy, but maybe it's not easy at all. It's pretty tough. We need to find something that reacts with either silver ions or chloride ions. And so we need chemical properties of these. Well, it turns out silver ions will react with ammonia. Silver ions actually like ammonium. This is a Lewis acid-base reaction to form a complex. And how many ammonias does it react with? Well, it looks like it reacts with 2 ammonias. So silver ions reacts with 2 ammonias. This forms the complex. This complex is very stable. This K is quite big, very big. And so what we have here is a very small K and a very big K. If the very big K, if we add these 2 equations here and the very big K's can compensate for the very small K, then we can get this reaction to go. And that's exactly what happens here. In other words, this delta G is positive, this delta G is negative, highly negative. And if we add these 2 reactions, we could get a net negative delta G. And that's exactly what's going to happen. The silver chloride solid plus 2 ammonia goes to this, which we call the diamine silver ion. Delta G is going to be less than 0 for this. So this is the reaction that occurs here. This one. Okay, in the next one here, which we regenerate the silver chloride precipitate by adding HNO3. The purpose of the HNO3 is this. And so here we'll take the solution from 2 plus HNO3, and then we get white PPT. That would be the observation. And the equation for this one is going to be, the different ways we can write the equation for this. One way is, one way of visualizing this particular reaction is Le Chatelier's. If I have an equilibrium here, actually in this case there's no solid left over, so this is shifted all the way to the right here. But if I wanted to reverse this, I need to do what? If I want to shift this back to the left, I need to either increase the product concentration or decrease the reactant concentration. One way of decreasing the reactant concentration is just get less ammonia. However, silver chlorides appear solid. And so, you know, the concentration doesn't change with pure solid, so I'm not going to mess with that. So how can I decrease the ammonia? Well, one way I could decrease ammonia is by heating it up. If I heat it up, the ammonia gets driven off as a gas, gaseous vapor. But I don't want to heat it up because heating things up is a hassle. I'd rather attack ammonia chemically. And so what can I use to attack ammonia chemically? Ammonia is a base, and so I want to use an acid. And so I just attack it with some nitric acid. And what that's going to form is 2-ammonium. Ammonium is not ammonia. These are totally different. Ammonium is an acid, ammonium is a base. So this is a very favorable reaction because we're going from a stronger acid, nitric acid, to a much weaker acid, ammonium. We've got a good driving force for this. And so what this is going to do is it's going to take out ammonia and then shift this, Le Chatelier's. As the ammonia concentration decreases, it shifts this equilibrium back to the left and reprecipitates out my silver chloride. And so that's one way of visualizing that. Alternatively, we could just do it by chemical reaction. You know, we could just attack the complex here directly. The H pluses. Those H pluses will attack the ammonias as the ligands. There's got to be chloride around. There's chloride left over here from earlier. We never got rid of the chloride. So we'll end up with silver chloride solid plus 2 ammonium. It shifts it this way. Okay, so 2 ways of visualizing this last step here occur. All right, now we're done with this branch here. And this was a silver analysis. And once we hit the end here, then we say we're positive. This is a positive test for silver. All right, what's the next ion that we're going to analyze for? Iron, aluminum, and chromium. Okay. Now, keeping this together, you know, these no reactions are really critical as far as understanding the separations. You know, we had to have some react and some not react. And so for iron, aluminum, and chromium, we're going to do this. We're just going to follow one of them. Which one comes first? Just look at the flow chart. Which one comes first? The iron, the aluminum, or the chromium?
Iron.
The iron. And so next, we're going to look at iron 3 analysis. And what I'm going to do is to try to keep it simple. I'm not going to have all the ions together. I'm just going to follow iron from the very start of the flow chart to the very end of the flow chart. And so we're just going to follow iron along its path through the flow chart. And we're going to write out the expected observations and expected reactions, i.e. equations. And so for iron, we go all the way back to the beginning. And so for 1, we have our unknown, and this is going to sound repetitive, but I only did it once. Our unknown AQ plus HCl gave us NR, no reaction. And we know that iron 3 plus is not going to react with the chloride. It's going to give us NR. Okay, I already written that. That's the first step in the flow chart. What's the next step in the flow chart for iron? So iron is going to go on a separate branch than silver. And so what's the next step for iron?
Precipitate iron hydroxide.
With what precipitating agent? Sodium hydroxide. And so the exact same thing is going to happen now. Now what we have is this is going to be called solution 1. And so solution 1, which is not the solution 1 from silver analysis, but from iron analysis, we got this no reaction. Now we're going to add sodium hydroxide. Okay, in the flow chart you mark it 6 molar sodium hydroxide, however many drops, right? But we know that in this case we must precipitate out everything completely. And so what does that mean? That means you keep adding sodium hydroxide until nothing more precipitates. You have to be careful because some precipitates actually start disappearing if there's too much precipitating agent, like lead. But here we're going to go solution plus sodium hydroxide. We should get, what color is iron 3 hydroxide? It's a rust color. And so we get a rust precipitate. You guys see that? It tells you with the colors there. And so the equation for this is going to be, tell me. Well, I'll tell you. It's going to be iron 3 plus, which is in solution 1, plus 3 hydroxides, is going to give us iron 3 hydroxide, which is our rust precipitate solid. Okay. And so the first part of this lab, what we're going to do is we're going to get a sense of the chemistry of what's happening here. I'm doing it differently than I've done in past semesters. And so what you're going to do is you're going to work together or alone and then complete the observations and the chemical equations for iron, okay, on your own. Okay, if you need a hint or help, check with your neighbors. If not, come up and ask me. I'll try to help you out. All right, any questions on this? So complete this iron, and then we're going to move on to the next one, aluminum and then chromium. We're going to do it for all. And this is worth points. Okay?